All right, a couple things first. You can ignore any of these due dates that are on any of these handouts. I am using them from somebody else, and I did not change the due dates. I'm not going to talk about 1, 2, or 3, or 1 or 2 right now. There are not a lot of conversion problems in AP Physics C. What I want to walk you through is looking at the graphs. So, a couple of reminders from last year. We learned that to go from a position time graph to a velocity time graph, we are going to calculate the slope. To go from the velocity time graph to the acceleration time graph, again, we're going to look at the slope. To go back the other way, we looked at last year going from the acceleration time to the velocity time, that we're going to look at area. To go from the velocity time back up to the position time, we are going to look at area. This year in AP Physics C, we're going to add the calculus piece. So if you are in calculus already, or you took calculus last year, you know that the slope is similar to taking the derivative. The derivative is helpful when we're looking at graphs that curve, because it's really hard to take the slope of a curved line. So instead of slope, again, we're going to be doing derivative. And then eventually, instead of area, we're going to be looking at integrals. Okay, so I'll go ahead and put it up here. I don't have enough space on the other one. Okay, so we're going to be integrating things, and we're going to be taking the derivatives. For the most part, derivatives and integrals in AP Physics C are pretty straightforward, and they're not too difficult, but we'll talk about those later. Okay, so right now, to transfer a graph, I'm looking at this position time graph at the top, and I'm going to transfer it to a velocity time graph first. Take it in parts, okay? So I notice I have a change in my motion here at 4 seconds. So I'm going to put a dotted line there to help me visualize that on the velocity time graph. And the next time my motion changes is at 10. So I'm going to put a dot at 10 there. I also have to worry about these same things on the acceleration time graph, because not only is my velocity changing at those time intervals, but also my acceleration is as well. All right, so now I'm going to look at this segment right here. That's a straight horizontal line. So we learned last year that that is constant velocity. It's a constant slope. It's a constant velocity. It has a positive slope, so it's a constant positive velocity. And I can actually calculate that. So when I'm calculating velocity, it's the change in position over time. Yeah, I'm taking up some space over here, but to help you explain it to you. All right, so my final position, remember whenever you're doing the change in something, it's always final minus initial. That helps you keep the signs correct, whether it's supposed to be negative or positive. So I get 50 minus 10, and then my change in time is 4 seconds minus 0, which is my initial time. So I get a positive velocity of 40 divided by 4, or 10 meters each second. So on a velocity time graph, constant velocity is shown as a straight line, but now it's going to be horizontal because I'm going 10 meters each second for that whole time interval. Now I'm going to skip over here and look at the last one. That is maintaining constant position. That means over here my velocity is equal to 0. So I'm going to go ahead and draw that on my velocity time graph. All right, now I can worry about this little curved piece here. It looks like I go from a positive velocity of 10 meters each second to a velocity of 0. Means I slow down. On a velocity time graph, that means it's going to be a straight diagonal line. That did not work out very well. Let me try that again. Okay, it's hard to do with a stylus. Straight diagonal line like that, you get the idea. This shows me I have constant acceleration. The good news for AP Physics C is all of our accelerations are going to be constant. So on my acceleration versus time graph, I'm going to have all straight horizontal lines. So again, I'm going to do my annotations. So if this is constant velocity from 0 to 4, that means I have no acceleration. I'm not increasing my velocity. I'm not decreasing my velocity. Over here from 10 to 20, I have a constant velocity of 0. So I have an acceleration of 0 over here as well. The only place we have acceleration is here. So acceleration is defined as the change in velocity over the change in time. So to find my acceleration, I'm going to a final velocity of 0. I had an initial velocity of 10. I have a final time of 10 seconds and an initial time of 4. So I end up with negative 10 divided by 6, which is a negative 1.67 roughly meters each second squared. So on my acceleration time graph, I'm going to go ahead and draw in my 0 accelerations first. And then I'm going to draw in my negative 1.67 down here. And we are all done. We just translated our position time graph into a velocity time graph. We translated our velocity time graph into the acceleration time graph. You want to avoid trying to go from this graph over here. Too confusing, too difficult. Always go from the position versus time graph to the velocity versus time graph, and then the velocity versus time graph to the acceleration versus time graph to avoid any mistakes. All right, the next one we're going to do is we're going to go from a velocity versus time graph now to a position versus time graph and an acceleration time graph. Again, you can ignore these due dates because this is not due October 24th. This is due pretty soon. All right, you notice we have two graphs down here. They are missing labels. So let's get our labels on there right away. So I have our position versus time graph and our acceleration versus time graph. Remember, a graph that is fully labeled has both a variable or a quantity and the units that go with that quantity. So don't forget to do that when you're doing your graphs. All right, we're going to look up here at the velocity time graph. I'm going to do the acceleration versus time graph first because it's easier. So from A to B, we notice the velocity is not changing, so I have an acceleration of 0. From D to E, the velocity is not changing, so I have an acceleration of 0. All right, that means the only time I have a changing velocity or an acceleration that's not 0 is from B to D. This is a constant negative slope, so this has to be a constant negative acceleration. Again, acceleration is the change in velocity over the change in time. So we look at our final velocity, which is negative 2, minus our initial velocity, which is a positive 2. And we're going to divide that by our change in time. Our final time is 12 seconds. Our initial time is 8 seconds. So what I get here, if I add the opposite, is a negative 4 divided by 4, or a negative 1 meter each second squared. That is the acceleration this whole time interval. The acceleration does not change direction here. This is a constant negative slope. It's a constant negative acceleration. So I'm going to throw in my scale over here. It doesn't really matter what I do because I only have to go from a 0 and a negative 1. So I'm just going to do my scale like this. I also need to do my times. So I'm going to go by 2s, but I'm only going to mark every other one. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so that's to keep it from being super crowded down there. All right, so now I'm going to plot some points because it makes it easier for me. So it is 0 acceleration from 0 to 8 seconds. So from 0 to 8 seconds, I'm going to draw in my little plots there. Then it's 0 from 12 to 20. I'm going to draw in my dots. I'm going to connect those dots here. And I get my accelerations of 0. Then I need to put in my negative 1. My negative 1 goes from 8 to 12. I'm going to put my dots and I'm going to connect those and make my line there. So my acceleration versus time graph is now complete. All right, let's do this position versus time graph. So now I'm not going to look at slope on this graph. I have to look at area, okay? So I'm going to break this into 4 different figures. It has a rectangle right here with a height of 2 and a width of 8. That gives me a displacement of a positive 16 meters. I have another rectangle down here. This has a width of 8 and a height of negative 2. So this is negative 16 meters here for my displacement. Then I got to worry about these little triangles. Well, that has a base of 2 and a height of 2. So to find the area of a triangle, it's base times height divided by 2, or a positive 2 meters for that one. Again, height of 2, base of 2 gives me 4. Divide that by 2, and I get the positive 2 meters. This one down here, oh, I don't know why my arrow, okay. We have a base of 2 seconds, a height of negative 2 meters, or meters each second. So I actually get a displacement of negative 2 meters there. All right, that means in total in the positive direction, I need to move 18 meters. So my scale down here has to accommodate for all of that. All right, so I'm going to put a 0 here. That gives me 7 lines going up. So I got to go by 3s. 3, 6, 9, 12, 15, 18. I'm going to do every other one just to keep it from being crowded. Negative 6, negative 12, and negative 18 down here. All right, so now I'm going to plot my points. Oh, I forgot my scale and my seconds. Let's do that. So 0, I'm going to do the same scale I did for my acceleration, but I'm only going to label every other one for space reasons. All right, I'm going to do the same thing now. I know that it does not give me a starting position. So initial position is what? We don't know, so we're going to assume it's 0. It makes our lives easier. Then we're going to go forward 16 meters, and we should be at positive 16 meters at 8 seconds. So that's going to be somewhere around in here. Then I'm still going forward. I got to go forward another 2, and I need to be at that at 10 seconds. So I need to be at a positive 18 here in 2 seconds. Then I'm going to go back the way I came for 2 meters because I had the negative 2 meter displacement there. So basically at 12 seconds, I'm going to end up back at that 16 meter mark. Then I'm going to go back another 16. So at 20 seconds, I should be back at 0. So I'm going to put my dot there. All right, now we need to draw in what the lines look like. All right, so let's draw in our lines. All right, so this is constant velocity. Constant velocity for this part means that we have a straight line on our velocity time graph. So I'm going to draw a straight line from my 0 seconds to my 8 seconds. Constant velocity. I have constant velocity again over here. So again, I know that's a straight line. All right, so the tricky part is for this piece in the middle. So we know that we are slowing down because we're going back towards 0 here. So that should be a line with a slope that's decreasing. So it's going to go like that. And then down here, now I change directions and I'm going back towards the origin. And my velocity is increasing because I'm going away from 0. So I'm going to curve down. So decreasing slope means a decreasing velocity. Increasing slope means an increasing velocity. We know this is acceleration and not constant velocity during that time interval there. So our lines are curved on a position time graph. I hope this helps some of you out. If you still have questions, please let me know. I will have the answer key for this posted in Canvas as well, so you can go check your answers. Have a great day, guys.